In this video, we're going to look at finding the derivative using difference quotients. What that long and maybe relatively confusing title really means is we're going to use the definition of the derivative that we're most commonly associated with here to find the derivative and use it as a function. In the previous sections, we have used it more or less as a place to plug in values. We've defined f prime of x as this and say find the slope of the curve or find the slope of the tangent line at some x value, and we plug it into our function with also this h in the appropriate places. But what we are doing now is we're finding the derivative of our function in general using this definition as a whole, and then at that point evaluating where our slope is equal to a certain value, and in this case is equal to -30. So the first step in our process is illustrated here by part 1 of the question. What we have going on here is we're going to find the derivative using the definition, like I said. And just like in the last video, we talked about not really needing to notice any more about the discrepancies because we're in more the general sense of the derivative, using it as a function instead of a place to plug in values. So we can take the derivative without having to worry about discontinuities, holes, and all that kind of good stuff, because if they're not defined in our function, they're not defined in our derivative as well. And in this case anyways, this is a cubic, which we know to be continuous for all real numbers. Okay, so what we're going to do is we're going to take the derivative f prime of x to be the limit as h approaches 0 of f of x plus h minus f of x over h. So what this translates to in our problem is still the limit as h approaches 0. F of x plus h is going to take the form x plus h cubed minus 57 times x plus h minus 7. And that's our f of x plus h right here. So then we're going to subtract the entire f of x. So we're going to put it in parentheses so we know to distribute this negative in there. So we get x cubed minus 57x minus 7. And this is all going to be over that single h here. When I do a quick mental pass to the limit test, I know that we're going to get x cubed minus 57x minus 7. And when we distribute this negative in there, all of that's going to cancel out to 0. We'd get 0 over 0. So this returns an indeterminate form. So we go about seeing if we can manipulate our function in different ways that we know and have done before. So here, we're still going to have the limit as h approaches 0. What we're going to do to manipulate this is let's actually take care of multiplying out x plus h cubed and do any distributions that we have here to see if any of our terms in the numerator can cancel and go away and make our function something easier to deal with. So x plus h cubed can be rewritten as x plus h times x plus h times x plus h, just expanding that out a little bit. Then taking care of this distribution here, we get minus 57x minus 57h minus 7 minus x cubed plus 57x plus 7. Almost forgot the x there. And again, this is still all over h. And even before we do this multiplication of these three binomials here, I see that minus 57x plus 57x goes to 0, minus 7 and plus 7 goes to 0 in the numerator. So all we're left with are these two terms right here. So now let's take care of multiplying out these three binomials here and see what we're left with. So again, we still have limit as h approaches 0. The first binomial multiplication will become x squared plus 2xh plus h squared. And again, we're still having to multiply this times x plus h. So then again, we still have minus x cubed minus 57h in the numerator after we cancel out all those other terms. And this is still going to be over h. So equivalently, limit as h approaches 0. Take care of this multiplication one more time, which involves distributing x plus h to every term here. So what we're going to get is x squared plus 2x squared h plus xh squared plus x squared h plus 2xh squared plus h cubed minus x cubed minus 57h. So we have all this string of terms in the numerator, and we're still over h. So now let's look at seeing if we can also subtract away some terms that have the same value but maybe have different signs about them. I just realized this is supposed to be a cubed here. Supposed to have cubed. Okay. So I see here, looking at this x cubed, we have an x cubed and a minus x cubed. So these can cancel and go away. let's see here, what else can we combine? We have a 2x squared h and a 1x squared h. So we can combine those terms. So the limit as h approaches 0. So 2x squared h plus x squared h gives us 3x squared h. And then we have xh squared plus 2xh squared. So again, we have 3xh squared. Added two of those terms, and we get plus h cubed minus 57h. So this is what we're left with at this point. And at this point, what I notice is that each term in the numerator here has an h in it. And I know that I have an h on the denominator. So in hopes that I can divide these two, the h's away, and make this something not over 0, I'm going to go ahead and factor out those h's out of each of these terms. So we still have the limit as h approaches 0. But we're going to factor an h out of each term of the numerator. So we're left with 3x squared plus 3xh plus h squared minus 57. And this is still over h. And like we said, since this is a factor of multiplication divided by another factor in this division, can divide these away. So what we're left with now is the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 57. And at this point, what I'm going to do is, since I've simplified this as basically as I can, I've manipulated it enough, I'm going to do another pass the limit test for h approaching 0 and plug in 0 for h. So here what that leaves me is 3x squared plus 3x times 0. This term will go to 0 plus 0 squared, which again, this term will go to 0, minus 57. So all we're left with is 3x squared minus 57. And at this point, we have our derivative. So we know that f prime of x, or the derivative of f with respect to x, is 3x squared minus 57. And just as we mentioned in the previous video for this section, we also have an equivalent form of the definition of a derivative, and it looks like this. We have f prime of x equals f of z, or actually it's not just f of z, that's the whole point of this. It's the limit as z approaches x of f of z minus f of x over z minus x. And as we said before, these two definitions, the one that I used in this problem and this definition, are equivalent. You can use either one of them in any form or fashion that you like. It depends on whether you think one of them is going to be easier to use than the other for a given situation. It doesn't really matter. They will lead you to the same answer. They will follow basically the same blueprint of question, but it's going to involve just a couple different changes in the steps that you do here. So you can use either one of them. It does not really matter. You would still arrive at a derivative that looks like this. And so now that we've satisfied part 1 of our question, which was finding our derivative, we need to go back and look at what part 2 of our question was, which says we want to find the values of x for which the tangent of f has slope, which means the derivative is equal to negative 30. So what we're going to do for part 2 is set our derivative equal to negative 30. So we're going to write that down. So we have f prime of x equals negative 30. And this is, as we said, part 2 of our question. So we have this, but f prime of x we just found to be 3x squared minus 57, and we're saying that equals negative 30. Okay, so we're trying to find values of x that make this statement true. So let's solve for x. The first thing we want to take care of is adding this 57 to both sides to get rid of it. So we do that, and we get that this is equivalent to saying 3x squared equals 27. Because negative 30 plus 57 gives us 27. And now what we're going to do is divide this 3 away. So we divide by 3, and we get x squared equals 9. Now to solve for x at this point, we're going to take the square root of both sides to cancel out that power. So we get x equals the square root of 9, which gives us x equals plus or minus root 3. And since we want the x values of a quadratic, x squared, that return 9, we want both plus minus 3. It's contrary to how we dealt with the square root function and only wanting principal roots. In this case, we defined our function that we're solving values for as a quadratic, and we know that there are two x values that return 9 when we graph a quadratic, namely plus or minus 3. So that's why we keep both the values, and both of these are legitimate answers.